example of a continuous beam using moment distribution method. Uh, in this example, both the far ends were fixed and uh, and these are the steps when the far end is fixed for moment distribution. Now, uh, now when the far end is simple, then we have to make some modifications, or we have to carry out some additional steps for when the far end is simple and if we have overhang beam. So, so we'll take an example of both these cases now. Let this be A, this be B, C, and we have a central point load of 80 kilonewton and we have a central point load of 100 kilonewton on segment BC. This is 4 meter, this is 4 meter, this is of course 2 meter, 2 meter, this is also 2 meter and 2 meter, and PI is constant for this example. Okay, so let us solve this. Here we can see that this C end is a simple support. So there will be some change in the distribution of moments, because we know that simple support cannot take any moments. So we have to balance. We have to release this joint. Release the moments from this joint. So step 1. Restrain the beam and find widths and extents. So let us restrain. This is 80 kilonewton and this is 100 kilonewton. Let this be MF AB, this be MF DA, this be MF DC, and this be MF CB. This is A, this is B, D, and C. This is 4 meter, 4 meter. MF AB will be equal to minus 80 into 4 by 4 by 8, that is minus 40 kilometer meter. MF BA 80 into 4 by 8, 40 kilometer. MF BC will be 100 into 4 by 8, so that will be minus 50 kilometer meter. And MF CB will be equal to 100 into 4 by 8, that is 50 kilometer meter. Now next step is to find the distribution factor. So for that, let us make a table. Let this be joint A, joint B, and joint C. Okay. So, joint order stiffness, total stiffness, and distribution factor. So joint A is connected to member AB. The stiffness of that member is 0. The distribution factor of that will be 0. Here you can add a column remark wherein it is a fixed support. You can mention it is a fixed support. Then B, it is connected to BA. And BC, stiffness here will be 4EI by L. So 4EI by 4, that is EI. And for this C joint is hinge joint, so it is 3EI by L, that is 0.75 EI. So the total stiffness will be 1.75 EI. So you can find the distribution factor, which is equal to Ki by sigma Ki, where this is total stiffness is sigma Ki, okay, and this is Ki. And you can say this is sigma and Ki. So the distribution factor at joint B that is 0.571, and for this will be 0.429. Note that the sum total of these two should be equal to 1. 0.571 plus 0.429 should be equal to 1, because it is the fraction of the uh, moment to be shared among the members. So sum of all these fractions should be equal to 1. Then at C, is connected to member CB. Here this time it will be 1 because it is hinge support. Okay. So we have the distribution factor. Now next step is to distribute the moments. So for that again we make a table. Joint A, B, C. Here we mention the joints and we mention the members connected to that joint. So this is connected to AB. B is connected to BA and BC. C is connected to CB. Next, we write the distribution factors of these members. So for this member, distribution factor is 0. For this, the distribution factor is 0.571, and for this, the distribution factor is 0.429, and distribution factor for this is 1. Next, we write the friction moments. So the friction moment here is minus 40, here it is 40, minus 50 and 50. You can see here it is minus 40, 40, minus 50, 50, and the distribution factor is 0.571, 0.429. Okay. Now here you have to do one extra step here, which is release and carry over, because this joint cannot take moment because it is a hinge joint. C joint is a hinge joint, so we have to release the moments. So here the unbalanced moment is 50, and if we don't release it, it will go on distributing, and at the end we will end up with some moment at joint C, which is not possible because joint C is hinge joint and it cannot take any moment. So we have to release this. So we apply minus 50 moment, and then we carry forward this to the far end. So that will be minus 25. Half of this will be carried forwarded here. So now your initial moments will be this will be 0, this will be minus 75, this will be 40, and this will be minus 40. Now with this initial moment we carry out our carryover distribution cycle. Okay, so same as earlier, now we will distribute, then carry over, distribute and carry over. We'll repeat these steps until the desired accuracy is achieved. So let us do the first cycle, that is distribution 1. Here the unbalanced moment is 0, so that will be 0 into 1, it will be 0 only, so it is 0. Now here the unbalanced moment is 40 minus 75, that is minus 35. So minus 35 is the unbalanced moment, so you have to balance this, so it will be opposite of that, means opposite sign of that is 35 into the distribution factor, that is 0.57, 0.571, so it will be 19.985 for this member, and 0.429 multiplied by 35, that is 15.015 for this member. Now the distribution factor here is 0, the unbalanced moment is 40, so 40 into 0, that is 0, so again this will be 0. Now we do the carryover. So carry over this moment, so this will be carried forward, half of this will be carried forward here, that is 0, half of this will be carried forward here, half of this will be carried forward here, half of this will be carried forward here, so half of this will be 0 only, and this cannot take the moment, so it will be 0. This won't be forwarded here because it is in support, so it will not be carry forwarded here, only this moment will be carry forwarded, and this will be carry forwarded here, that is 19.985 by 2, that is 9.9925. Okay, so here you can see that these are both are 0, so unbalanced moment is 0, so we can stop here. So there is no unbalanced moment, so we no need there is no need to carry carry out the distribution carryover cycle. So your final moments will be 0 here, here it will be minus 75 plus 15.015, that is minus 59.985 minus 59.985. On this side it will be 40 plus 19.985, that means 59.985. On this side it will be minus 40 plus 9.9925, that will be minus 30.0075. So these are the final moments. You can also see that here summation of moments at B is also 0, because the left hand side moment and right hand side moments are equal and opposite. So this is your equilibrium check. Clear? Now you can also do the shear checks or shear correction. To draw the shear force diagram. So for that you need the shear force values, the freely supported value, and so here in continuation only we are calculating that. This is A, this is B, and this is C. Here shear corrections, AB, free shear. Free shear means you have to find the freely supported shear value of shear force due to freely supported condition. So here this is 80 kilonewton, this is 4 meter. So the this will be 40 kilonewton and this will be 40 kilonewton A and B. So at A, this free shear will be 40, here it will be 40, and for second segment it is 60 kilonewton, 4 meter. So this will be, wait a minute, 100, it is 100 kilonewton. 100 kilonewton. So this will be 50 kilonewton. This will be 50 kilonewton. So 50 and 50 here. Now the shear correction, will be due to the unbalanced moment in the span AB. The unbalanced moment in the span AB will be, let us write the unbalanced moment. So the unbalanced moment will be minus 30.0075 plus 59.985. So that will be equal to 59.985. That will be 29.9775. kilonewton meter. So this is the unbalanced moment. Now, and the positive sign shows that it is clockwise. So this is clockwise. So the reaction resisting this moment will be in anti-clockwise. So we'll have anti-clockwise here. So this will be 29.9775 divided by L, that is 4, and this will be 29.9775 by 4, that will be 7 point. So here it will be minus 29.9775 by 4, which is equal to 7.494, and on this side it will be 29.9775 divided by 4, that will be 7.494. Similarly, on this side, the unbalanced moment is minus 59.85. That means we have an anti-clockwise moment, moment on this span, which is 59.985 anti-clockwise. So this is anti-clockwise. This tries to rotate the beam in anti-clockwise direction. So the reactions will form a clockwise couple like this. So this couple will resist the anti-clockwise moment. So this will be 59.985 divided by 4. This will be 59.985 divided by 4. So here this will be positive 59.985 divided by 4. This will be minus 59.985 divided by 4. 59.985 divided by 4. So that is minus 14 point. This value is equal to minus 14 point minus 14.996. This value will be 14.996. Okay, so the corrections for shear are done. So the final shear will be sum of all these shear forces. Final shear will be equal to, it will be sum of these two. You sum of this or sum of this, same, it will be same. 50 minus 14.996, that is 35.004 kilonewton. This will be 50 plus 14.996, that is 64.996. This will be 47.494, and this will be 40 minus 7.494, that is 32.506. kilonewton. Now you can take the summation of all these. So summation of all these will be equal to 32. This is our static check. So if you want to check whether the reactions obtained are okay or not, so for that you can do a static check, so in which we add all the forces. So summation of all the reactions will be equal to 32.506 plus 47.494 plus 64.996 plus 35.004. So the total will be 32.506 plus 47.494 plus 64.996 plus 35.004, that is 180 kilonewton. And the total load on the beam is equal to total load is 80 plus 100. Okay, the total load on the beam is 80 plus 100. This total load is 80 plus 100. 80 plus 100, that is 180 kilonewton. So this implies static check is okay, because total load is equal to reaction, so there is no discrepancy in your shear values, so therefore it is okay. Now you can draw the shear force and bending moment diagram in the next step. Shear force diagram and bending moment diagram. Now to draw the bending moment diagram, let us first write all the values here. The value of moment at A will be minus 30.0075. Minus means it is anti-clockwise. So anti-clockwise 30.0075 kilonewton meter. Then at joint B on left side, the moment is 59.985. 59.985 kilonewton. And on the right hand side, the moment is and negative, means it is anti-clockwise. This is joint B. This is A and this is C. This moment is also 59.985 kilonewton, and the moment here is 0. A kilonewton meter. 0 kilonewton meter. Now we write the reactions. So the reaction at A is 30.0075 32.506 kilonewton. The total reaction at B will be 47.494 plus this value 64.996. So total will be 47.494 plus 64.996, that is 112.49 kilonewton. Okay. Sum of these two will be the total reaction at B, and here the reactions will be 35.004 kilonewton meter. Now you can easily draw the shear force and bending moment diagram following these forces. So let us first draw the bending moment diagram. So this arrow is pointing this A point on upward, so we follow this point. So this will be upward. This is 0 here. Here it will be 30.0075. At B, it is again pointing this upward. So it is 59.985. This arrow is pointing it upward. So again it is here only. Then here it will be 0. So this is the diagram for the continuity or fixity. Now due to freely supported moments, so let us find the freely supported bending moment. So M max freely supported for the segment AB will be equal to 80. This is 4 meter. 4 by 4, that is 80 kilonewton meter. And for the second segment, which is 100 kilonewton, BC 4 meters span. So M max freely supported will be 100 into 4 by 4, that is 100 kilonewton meter. So you can now plot this moment on this. So at set midpoint where there is point load, it is 80. So here it is 80. So you connect this by a linear line. Okay. Then here it is 100. Again, since it is a point load, variation of the bending moment diagram will be linear. Okay, so I think the portion below this line is negative and above this is positive. This is positive and this is negative. So this is your negative moment, zone of negative bending moment. This is positive bending moment. This is negative zone. And this is the positive portion. So this is your bending moment diagram. So you can omit this line also. This is your bending moment diagram. BMD. Now we draw the shear force diagram. For shear force diagram, you have to follow the load. See, our sign convention for drawing the shear force diagram is clockwise shear as positive. Clockwise shear as positive. That means if we are moving from left to right, the upward force is positive. So let us move from left to right. So as we are just to the left of A, we are here. The shear force is 0 because there is no force. As you just cross point A, this upward force is acting, and as per sign convention, upward is positive. So this will be 32.506. Then as we move, there is no load, and then at mid span there is 80 kilonewton point load. So 32 minus 80, 32.5 minus 80, 32, 32.506 minus 80, that is minus 47. So at this, up to just left of this point, the shear force is 32.506, and just to the right of this, the shear force will be 47.494. Okay, and this will be constant. Okay, so the diagram would be like this. Just on the left side of A, there is no force, so it is 0. Just to the right of A, it is 32.57, and as we move ahead, this will be constant, and up to just to the left of point this point load. Okay, and as we just cross this point load, this 80 kilonewton point load will be acting. So 32.506 minus 80, so it will be 47.494. Okay, then now as we move ahead towards point B, there is no load, so this will be constant. But as we just cross this point A, the reaction will come into picture, the reaction at B. So that reaction is 112.49. So minus 47.494 plus 112.49. So that will be 64.996. So here the reaction will be 64.996. Just to the right of point B. Okay. Now as we go on, this will be constant. So this will be constant up to the left of point A, point load 100 kilonewton. And as we just cross this 100 kilonewton point load, this 64.996 minus 100. So that will be 74.486. Wait a minute, we made some mistake, I think. 32.506 minus 80, 37 from this plus, okay, so 64.996 minus 100, so that will be 30. So minus 100, so it will be minus 35 point, up to just to the left of this point load, it will be 64.996. As we cross this point load, this will be 35.004, and this will be constant up to the left of point C. As we cross this point C, this reaction at C will come into picture, that is 35.004. So minus 35.004 plus 35.004, it will be 0 here. Okay, so this is your positive shear force diagram. This is negative, and this is positive. So this is the positive shear force diagram. This is positive shear force diagram. And this is negative shear force diagram. So this is how we can draw the bending moment diagram or shear force diagram. Okay, so with this, this example is over. Now we'll take one more example in which we have the overhang case. We have a beam with overhang. There is a UDL on this span. (40 kilonewton per meter). At this be A, B, C, and at D we have a point load of 30 kilometer. Okay, and EI is constant for all the members. Okay, so let us solve this. Now here also you have to make some changes in your distribution cycle. So here, see what change was there from the previous example. This is the change in the previous example. This is the change you have to do. This is the additional step you have to carry out when we have simple end. Now here we have overhang beam. So the additional step we will discuss. Step 1 is restrain the beam, and find friction actions or friction moment. Note that this beam can be treated as equivalent to this is equivalent to equivalent beam will be you can treat this as beam A, B, C, which is loaded with a UTM of 40 kilonewton per meter. Now this point load is to be transferred here, so it would be 30 kilonewton point load at point C along with a moment of 30 into 2, that is 60 kilonewton meter. 30 into 2, that is 60 kilonewton meter. This is point C. Okay, so this is the equivalent beam or equivalent load diagram on given beam. Okay, you can simplify this way. So you can now find the friction moments. Note that these 30 kilonewton and 60 kilonewton meter are the joint load and joint moment respectively at joint C, so which will not be used here for finding the friction actions. This is A, this is B, B and C. This is 4 meter. This is also 4 meter, 4 meter, 4 meter. You can now find the peaks and moments for this. Let this be MF AB. Let this be MF BA. Let this be MF BC, and let this be MF CB. So MFAB will be 0 because there is no load on span AB. MFBA is also 0 because there is no load. MFBC will be equal to minus 40 into 4 by 8. 8 by 12 square, sorry, it is real. 40 into 4 square by 12, that will be minus 53.33, and MFCB will be 40 into 4 square by 12, that is 53.333 kilometer. Next step is to find the distribution factor. For which we make a table. Join, join, number, stiffness, total stiffness, and distribution factor, which is equal to Ki by sigma Ki and sigma. So, joint A, it is connected to member AB. Here it is a fixed joint, so distribution factor is 0 because it is fixed support. Then the joint B, it is connected to member BA and it is connected to member BC. Now BA is 4 meter with par and fixed, and BC is also 4 meter in length with par and simple. So this here it will be 4 EI by 4, that is EI, and here it will be 3 EI by 4, that is 0.75 EI. So sum total of these two will be 1.75 EI, and the distribution factor will be same as earlier, 0.571 and 0.429. Okay. Same at joint C, it is connected to member CB, but it is a hinge joint, so distribution factor will be 1 because it is hinged joint, hinge support. Okay, so we have the distribution factors for all the members. Now we distribute the moment. So next step is moment distribution. So we first mention the joints A, B and C. Here we write the joints, then we write the members connected to joints. So here it will be AB, BA, BC, CB, and here CD. This point is D point. Okay, this is D point. Now let us write the distribution factors for these moments, these members. So 0 here, it is 0.571, 0.429 here, distribution factor 1 here, and dash for this number. Then we write the friction moments. So the moments 0 here, 0 here, minus 53.333. Here it is 53.333. So this is the friction moment. Okay. Now we have to release this moment same as earlier because it is now it is simple support, this one. So C is hinge support, so we have to release that. So next step will be to release and carry over and carry over. So this will be minus 53.333. Okay, and here half of this will be carried forward here, that is minus 26.667 will be carried forward here. So this will be 0 now. This will be some value, but now the overhang moment and carry over. We have to carry over the overhang moment as well. Overhang moment and carry over. So the overhang moment here it was it is minus 60 and plus 60 here. Now this moment should, will also be will have to be balanced, will have to be carried forward to the far end. So 30. Okay. So now your initial moment will be minus 60 on this side, this will be plus 60, on this side it will be minus 53.333 minus 26.667 plus 30, so that is minus 50. So here it is minus 50, 0 here, 0 here. These are your now initial moment. So when you have overhang case, you have to not only carry, you have to release and carry over for the parent simple, but also you have to carry over the overhang moments. So this will be your additional steps. Okay, now you repeat the distribution carryover cycle. So your first distribution, so here the unbalanced moment is 60 minus 60, 0. So it is 0. Okay, so this will be 0 only. Now here the unbalanced moment is minus 50. Okay, so this is to be distributed among these two members. So the distribution factor on the left hand side is 0.571. So 0.571 into 50, that is 28.55. So this number will have 28.55, and on the right side it will be 21.45. This will be 0. Okay, so this is your first cycle. Now we carry over the moments. Now this will not be carry forwarded here because it is hinge support. So only this will be carry forwarded here. This will be carry forward here. This will be carry forward here. Note that this is fixed support, so it can take the moment. So half of this will be carry forward. 28.55 divided by 2, that is 14.275. Okay, and here it will be dash. So here you can observe that there is no unbalanced moment left. So you can stop the cycle here. So your final moments will be minus 60 plus 60 here, then here it will be minus 50 plus 21.45 minus 50 plus 21.45, that is minus 28.55, here 28.55, and here it will be 14.275. So these are the final moments. Then you can also do the shear corrections, same as earlier we do. So for shear corrections, first write the pre-shear. So the value of free shear, see this span is there is no load on this span, so free shear will be 0 at A and B for segment AB, and free shear here it will be 40 into 4, that is 160 by 2, that is 80 kilonewton here, 80 kilonewton here. So free shear with 40 kilonewton per meter loading with 4 meter span, the value of this shear force will be 80 kilonewton, 80 kilonewton. So this is 80, this is 80. Now there is no load on this one, it is 0 and 0. Next step is shear correction. So the unbalanced moment on this span is 0, so shear correction will be 0 here only. Oh, not 0, sorry. The unbalanced moment is this is 14.275 and this is 28.55. So total is 14.275 plus 28.55. So for this span, the unbalanced moment will be 14.275 plus 28.55, that is equal to 42.825 kilonewton meter. Okay, and similarly for this span, the unbalanced moment will be 60 minus 28.55, 60 minus 28.55, that is 31.45. So now this is also clockwise, this is also clockwise, so that, and the reactions will be in anti-clockwise direction. So anti-clockwise means this will be upward, this will be downward, and for this span also this will be upward, this will be downward. So this shear correction, and this is 4 meter in length, this is 4 meter, this is 4 meter. So the shear correction here will be 42.825 divided by 4. Here it will be minus 42.825 divided by 4. On this side it will be minus 31.45 divided by 4 and 31.45 divided by 4. So this value will be 7.8625. This will be minus 7.8625. This will be 42.825 divided by 4, so it will be 10.706. It will be equal to 10.706, and this will be equal to minus 10.706. So your final shear will be 87.8625. This will be 80 minus 7.625, 625, That will be 72.1375. This is 8. And here it will be 10.706, and here it will be minus 10.706. Okay, you can also verify. See, note that here the equilibrium check is okay. Sigma m v equals to 0. Sum of the moments equals to 0. This is your equilibrium check that you have to check. Sum of moments at B equals to 0. 28.55 minus 28.55, it is 0. Same way, here we will do static check. So for static check, summation of all the reactions will be equal to minus 10.06 plus 10.706 plus 72.1375 plus 87.8625. So sum total reactions will be it is 160 kilonewton. Okay, and the total load is UDL of 40 meter span, 4 meter span, 40 kilonewton intensity. So it will be 160 kilonewton. So it is okay. Total applied load equals the reaction. So your static check is okay. Okay. Now finally we draw the shear force and bending moment diagram. Bending moment at A is on left of A it is 0, on just right of A it is clockwise 14.26275. Let me just write the moments. This be A point, B and C, this is D. So the moment here is at A is clockwise 14.275, kilometer meter. Just left of B it is 28.55, on just of right of B it is minus, means anti-clockwise 28.55. Left of C it is clockwise 60, and right of C anti-clockwise 60, and here it is 0. Okay, now the reaction at A, B and C. Note that here you have to add the overhang reaction also. So you have to add the overhang reaction or overhang load. overhang load. So 30 kilonewton load will be added to this. This is the overhang load. This load. Okay. It is transferred from point D to point C. So that has to be added. So plus 30 will be the load. So total will be 87.8625 plus 30, that will be 117. 117.8625. So same thing should be reflected in the static check also, because we have considered this equivalent beam only, but in totality when we draw the shear force bending moment diagram, we have to draw the bending moment and shear force diagram for this complete beam, not for the equivalent beam. So let us add this also. So plus 30. So total load will be 190 kilonewton. Same way adding 30 kilonewton load here also, plus 30, so that will be 190 kilonewton. So the reaction here is minus 10.706. So minus 10.706. That means it is actually acting downward. Okay. Then at B it is 10.706 plus 72.1375. So total will be 0.706 plus 72.1375, that is 82.8435. Okay. Same way here it is 117.826. See, you can add this on this side also, just to the left of A instead of here. So the total here it will be like this. So it is 117.8625, 117.8625. Okay, so this is the values of the reactions. Now you can draw from this, you can draw the shear force and bending moment diagram. Bending moment just to the left of A is 0. Bending moment just right to the A, it is 14.275. Now it is in clockwise direction, so the arrow is pointing this point A downward, so it will be here 14.275. Now this is pointing this point upward, so here it will be 28.55. Okay. Then this is again pointing it upward, so this is 60. and here it will be 0. Now we can connect this. Now on this one there is no now we draw the freely supported bending moment, superimpose the freely supported bending moment on this. So for the first segment there is no load, so it will be 0, and on the second segment it is loaded with UDL of 40 kilonewton per meter. 4 meter is the span, so the maximum bending moment at mid span will be Mmax freely supported condition will be equal to 40 into 4 square by 8, that is 80. So here it will be 80 parabolic. So this is 80 kilonewton from here, but you have to interpolate this value also. So this is your bending moment diagram. The value here will be, oh wait a minute, we have drawn it wrong. This is point C, so parabola will be this will be your positive value. Anything above this is positive, below is negative. This is positive and this is negative. And this value you have to interpolate 28.55 plus 60 by 2 deducted from 80. So your positive moment at the mid span will be 35.725. Okay. This is your VMD diagram. Now we draw the shear force diagram. Simply follow the load. It is minus 10.706, so it will be minus 10.706, so downward. See, our sign convention for this is clockwise as positive. For this, the sagging is positive. This is our sign convention. Then as we move, there is no load. As we move up to the left of point A, it will be constant. And as we just cross this point, there will be an upward reaction. Which is equal to 82.8435. So minus 10.706 plus 82.8435, that is 72.1375. Okay. Now as we go, now there is a UDL. So as we move, the load will keep on decreasing. The shear force diagram will keep on decreasing up to point left of point C. So up to left of point C, the value of the shear force will be 72.135 minus 40 into 4. That is minus 87 point, somewhere here, minus 87.8625, and it will keep on varying linearly. Okay. Now just to the left of, just to the right of C, as we just cross this 117.8625 load will come into picture. So plus 117.8625, so it will give you plus 30. So plus 30 somewhere here. So plus 30. Now this 30 will keep on, will be constant just to the left of this point load. Keep on constant up to just to the left of point, just to the left of D point. Okay. As we just cross D point, this 30 kilonewton will come in downward direction. So this will be 0. Okay. So this is your negative shear. This is positive shear, and this distance will be 72.1375 divided by 40. 40 is the intensity of the load, and this distance will be 87 point this value. Divided by 40, so that will be 72.1375 divided by 40. It is around 1.8 meter. Okay, so this will be 2.2 meter, around 2.2 meter. And you also have to find the corresponding maximum bending moment corresponding to this point of zero shear. So at this point of zero shear, your bending moment will be maximum here. So you have to find the maximum bending moment also. So that you find it at your end. Okay, or simply you can find it from the area of the area under the shear force diagram. So maximum bending moment will be equal to minus 10.706 into this span length, that is 4 meter, that is the area of this portion. Okay, now you add the area of this triangle. So this area of triangle will be 1 by 2, base is 1.8 into height is 72.1375. If you sum them, you will get the moment at the point of zero shear, that means at this point. So that will be it will be 22.224 kilometer meter. Okay. And this value should be less than that. Just verify this. Okay, this should be verified. Just check this value, because your maximum bending moment will be this much, 22.224. So this should be checked. Okay. Maximum bending moment is 22.224. Simply you can draw the bending moment diagram from the area under the shear force diagram. Simply just area, this is the moment here is 14.275 clockwise. So 14.275. Now you 14 point, wait a minute, this is positive value. 14.275 minus area under this rectangle, that is 10.706 into 4 minus 28 point. So here you are getting a moment of 28.55 minus 28.55, which is as per our calculation same. Then at this point, it is at D point, means at point of zero shear. At this point, it is 22 point. At D point, it is 22.224. So, and the variation will be parabolic, and the shear force is decreasing. So maximum slope here and minimum slope is here. So maximum slope here means it will be like this. Okay, and then you deduct this 22.224 minus area of this triangle. So that will be 1/2 into 87.8625 into 2.2. That will be minus 74.5. 4 minus 74.4. So somewhere here minus 74.424. So this will be like this. Okay, and then you add minus 10.7. Okay, and the moment here is then you have a clockwise moment here 60. So add 60 to this. So you will be somewhere here. And then wait a minute. Something is wrong here. 0.5 into 87.8625 into 2.2 96 point something minus 22.224. Wait a minute. Minus. Oh wait. Here we have not added this value. Maximum bending moment will be 14.275. Okay, that moment is not added here. 14.275 plus this value. So this will be 22.224 plus 14.275. So it is 36.499. Okay, so that is the moment. So this is 36.499. So this moment will be 36.499 minus 0.5 into 2.2 into 87.8625. So that is almost 60. So it is minus around minus 60, and this will very linearly and 0 here. This is your positive, this is negative. This will be the negative bending moment. This will be negative bending moment. So make the corrections you can draw this way also. So here this moment is actually 36.499. So this is correct. This is not wrong. This is correct. It is 35. It is less than that. So it is okay. So you can draw the bending moment diagram this way, or you can also draw in this way. And your shear force diagram, this will be the negative shear. Negative shear. And this will be the positive shear. So this is your shear force diagram. Shear force diagram, and this is bending moment diagram. Okay, so that's it for today. If you have any doubt, we can discuss now. Any doubt in this?